So welcome. So electric potential and electric potential energy, and I suppose my advice about this is just make really sure that you compare and contrast, and that you know the different definitions and how they are similar and how they are different to each other. Let's think about gravitational analogy. So we have this idea about a gravitational force. Could be the weight on a book, could be the pull of the Earth on the moon. And what we say is the force is experienced by one mass, say the book, or say the moon, due to its position relative to the other mass. Well, for the book it's the Earth, and for the moon it's the Earth. The Earth is like the mother charge for the two examples, and the book or the moon are like the little masses. And these are measured in newtons. And then we said, well, it'd be useful if we could actually just talk about the influence of the Earth at all points without having to put a mass there. So we came up with this idea about gravitational field strength, which was little g, and basically the gravitational force that a 1 kilogram mass would experience at that location. So here we have our mother charge. You can pick any location you like, and well, what's the force that a 1 kilogram mass would feel there? Well, what's the force that a 1 kilogram mass would feel there? Well, what's the force that a 1 kilogram mass would feel there? Well, it will have a direction, and if you're close to the Earth, it's reasonable to say it's going to be bigger. But you don't need to put the masses there. You don't need two masses for the gravitational field. The gravitational field is about the Earth, and it's there whether you put any masses there or not. So it's the gravitational force that a 1 kilogram mass would experience at that point. Not that it does experience, but would experience at that point. And that's in newtons per kilogram. And you probably learned that the G was 9.8 newtons per kilogram, I hope. You might have learned it was 9.8 meters per second squared, which is not true. It's different, let's say. It's not incorrect, it's just a different thing. And then we have the change in the gravitational potential energy. So, we say, well, my change, and U is energy. My change in gravitational potential energy is the change in energy stored in a mass due to its changing position relative to the other mass. So now I'm taking a mass and I'm moving it. And as I move to higher altitudes, I have to do work. You have to do work to lift this pen up. That work is manifest by having more potential energy inside this object. And so I say, well, okay, I do that by taking my force and multiply it by some distance. And you may recall that the distance had to be in line with the force and all that kind of stuff. There's no law saying the force had to be constant, but we started off with a constant force to begin with, but then we made it a bit more interesting. And that was measured in Newton meters or joules. And then we had this gravitational potential, not potential energy, gravitational potential, which was that effect that a 1 kilogram mass would feel if it was put there. So we have our gravitational potential change. Delta V is about points. Delta U must be about moving a mass. Delta V is about moving a point of interest. So they're kind of like similar but different. And this is in, well, it's going to be in Newton meter per kilogram, which would be joules per kilogram. And there's no special unit in gravitational theory for this, although for electrical we will see. So again, just using this gravitational analogy, we could talk about a uniform gravitational field. And there we see we have a mass and it's got a certain force. There's a lifting force. I move that lifting force through a certain distance and I get a certain amount of work has to be done. And that's a certain amount of change in potential energy. Yeah. But what happens when it's a non-uniform field? Well, okay. Then I got to do the same thing, but somehow I got to take into account that the force is bigger when I'm closer to the planet than when the force is further away. So whereas this was a constant force for the inside a room business, it's not a constant force for the near a planet business. So my math is going to be a little bit more complicated. I'm going to integrate the force with respect to distance. That's all I'm going to do. Rather than multiplying the force by a distance, I'm going to integrate the changing force with respect to distance. So, okay, not so bad. If I think in terms of electrostatics, I can do the same thing here. I have a big mother charge here, and I can have another charge, and I can talk about the force between them, or I can pick a point of interest and say what's the electric field at that point. I could imagine moving that second charge and say what's my change in potential energy, or I could imagine moving my point of interest and saying what's my change in potential. So. Now, for electric fields, I can make non-uniform and uniform electric fields. We've done one already. We did one in lab where we imagined a point charge which was positive and a point charge which was negative, and we had the equipotential lines, equipotential like electric potential, equipotential lines, and they're like contour lines on a mountain. So here's my visualization. It works for this little bit. It's not uniformly, it don't work for everything, but for this little bit, I imagine a positive charge is like a volcano summit, and I imagine a negative charge is like a sinkhole, and I imagine that my equipotential lines are like equal height lines, and then my electric field lines. Well, electric field, the electric field points from positive to negative charges, and so imagine rolling a boulder down the side of the volcano. And what I'll find, because in volcano land there's no friction, what I find is all these boulders will end up at the bottom of the sinkhole, but they'll take different routes. And the thing about the routes is the angle between the route taken by the boulder and the contour line is always 90 degrees. It's the same for these guys. They're always at 90 degrees. Yeah, I didn't draw it very well, but that's what's going on. And my argument is that if you know the field line pattern, you don't necessarily need to know where the charges are. You just need to know in your vicinity what do the field lines look like. I can make a uniform field the most easy way. I suppose I could get really close to a charge and I could just have a little variation in its dimensions. But probably an easier way is I just make a whole bunch of positive charges on one metal plate, a whole bunch of negative charge on the other metal plate, and then we just get the field between them. And you did that in lab as well, didn't you? You basically plotted out that field lines. There was a little bit of leakage around the edges, but, you know. And again, my three-dimensional analogy is here's the top of an embankment, and here's the bottom of the embankment, and you've embanked it nice and smoothly and evenly so that you have a steep slope, but it's a uniform steep slope. And that's what gives you a uniform field. So here's a bit of a better write-up of what I was doing. So gravitational force, a force to field, and change of potential to change of potential energy, change of potential. So if I want to go from force to field, I basically I didn't write them in, did I? If I want to go this way, I divide by little m. And if I want to go that way, I multiply by little m. And if I want to go this way, I divide by a little m. And this way I want to multiply by m. And over here I will divide by q, and I'll multiply by q, and I'll divide by q, and I'll multiply by q. Oh, I'm so sorry. I'm not looking at my things on my diagram. That's weird. I'm plotting this slightly differently. Let me get an eraser quick. And I just told you what's on the other axis. It's interesting. I didn't think I ever drew it this way. So if I want to go from the gravitational force to my gravitational field, I divide by m. If I want to go from the field to the force, I multiply by m. If I want to go from the gravitational potential energy to my gravitational potential, I divide by m. Gravitational potential to my gravitational potential energy, I multiply by m. And the same thing goes for this electrostatics. I either divide by q to go from force to field, I divide by q to go from electrostatic potential energy to electrostatic potential, and I multiply to go the other way. So a 15 kilogram mass weighs 45 newtons. When it is located near planet Bonaquisti, what is the gravitational field strength at this point? So let's visualize. So here's the planet. This is big M. And here's the little mass. And I know this is 15 kilograms. And it weighs, that means the pull of gravity on it is 45 newtons. When it is located near... I'm sorry. How do I turn you off? That's interesting. Sorry. Okay. So a 15 kilogram mass weighs 45 newtons when it's located near planet Bonaquisti. What is the gravitational field strength at this planet? So I say, oh, my gravitational field strength equals the force due to gravity divided by the little mass, which equals, well, in this case, it's going to be 45 divided by 15, which equals 3, and the units will be newtons per kilogram. See how we did that? We said, oh, yeah, the definition of gravitational field strength is the force that a 1 kilogram mass would feel. I have a 15 kilogram mass feeling 45, so 1 kilogram of it would feel 3 newtons per kilogram. Let's do an electrostatic version of it. So there's my Q, and here's my little charge. A 60 coulomb, 60 positive charge, experienced electrostatic force of attraction of 12 newtons. When located near a negative planet, minus Q, what would the electrostatic field be? Well, E is equal to Fe over Q, which equals, I look at my diagram and I go, well, 12 newtons over 60, which equals 1 over 5, 0.2 newtons per kilogram, newtons per coulomb. Man, those answers are completely messed up. Not even in electric field at that point. So same. So you can have big expressions for these things, but there's a simple relationship between them. A 30 kilogram mass is located at a point in space. Gravitational field strength at that point is 20 newtons per kilogram. What is the magnitude of the weight? So here's my, again, here's my big mass, and here's my little mass, and it's a 30 kilogram. And at that point in space, G is equal to 20 newtons per kilogram. I can cheat and say that because it's masses, it must be an attractive force. So what is the magnitude of the weight? I can say, well, Fg is equal to m times the gravitational field. So Fg is equal to 30 times 20. Fg is equal to 600 newtons. Now you know W equals mg. You've known it for a long time. But you probably didn't realize what you were doing. 24 coulomb positive charge is located, so here's a 24 coulombs positive, and it's located at a point in space. The electrostatic field and the electrostatic field at that point is E. E is equal to 6 newtons per coulomb. And what is the magnitude of the electrostatic force will the mass experience? That's a positive. Yeah. Don't tell me what direction. I'm gonna cheat a bit. I'm gonna say, well, there's my Fe. I don't know which way it is because I don't know what charge this negative was. this one down here was. But I do know that Fe is equal to E times Q. I should really say Q times E to make the analogy work, yeah? Remember, Q is like M and E is like G. So F equals mg, Fe equals QE. So Fe is equal to my charge. It's the charge of the little guy, which is 24, times E, and E is 6. So that would be 24 and 6. 4 carry 2, 144 newtons. Yeah. So just simple relationship there. Now let's do the other way. We're moving along a gravitational field line. So we're going to start imagining with uniform. So we say, well, here's my lifting force and here's my distance which I travel through. And if I want to know my change in potential energy, change in gravitational potential, I simply multiply I call it delta H here, and it's delta X there. So let's call that delta X. So if I want to get my gravitational potential energy, I simply multiply by my delta X. Take my force and I multiply it by my delta X. But the same goes over here. If I want to go from my gravitational potential, my gravitational field to my gravitational potential, I do the same thing. Yeah. Because how do I get from here to here? I divide by M, dividing F by M gives me G. So you want to go between force and field, multiply or divide by M. Want to go between potential energy and potential, multiply or divide by M. You want to go between force and potential energy multiplied by a distance. You want to go between field and a potential multiplied by distance. So try and really get that pattern, because then the rest is just math. Which way am I doing it? Electrostatically, well, same thing holds. I say my work, I can say, let's go back, I'm sorry. I said my work equals my change in potential energy, which equals my force times my displacement. In this case, I say my work is equal to my change in potential energy, which equals the force times my displacement. It's electrostatic force rather than a gravitational force, but it's still the same idea. So we say a 4 Newton mass is raised by 12 meters vertically upwards. So that's 4. So that's 40. So that's 40. 40. And this is F lift. And it's raised by 12 meters. What is its change in gravitational potential? My change in U is equal to work done, which equals to the force times my distance. They're in line with each other. So that's all I need to do. I say my work is equal to my work, which equals to my 40 times my 12, which equals 480 joules. We did that in Physics 1. Yeah, you did that in Physics 1. Why do I have 48 down? Oh, because, I'm sorry, 4 Newton mass, 4 Newton weight, isn't it? So 4, I need to change that. That's me cutting and pasting. So that's 4, which is 48. A positive charge experiences a 5 Newton electric force in a uniform electric field. So we'll have a Fe is equal to 5 newtons. The charge is moved 20 meters down a field line. So the charge is moved, I'll do it like that way. There's my field line. what is the change in electric potential energy? Delta U is equal to the work done, which equals to my force times my, let's call it S for one of a different letter. This is S. And this equals 20 meters. So my delta U is equal to W, which equals my 5 times my 20, which equals 100 joules. So again, you're just multiplying by, you're taking the force and you multiply it by the distance it moves through. I've got to be a little bit more careful about electric fields because gravity is always attractive, but sometimes we have repulsive forces and sometimes we have gravitational forces. Now, let me ask you a question. Let's think about our gravitational similarity. This is mountaintop. If a boulder runs downhill, is it increasing its potential energy or decreasing its potential energy?
Decreasing.
So delta U would equal 0, or would equal negative, yeah? If it was, in this case, we're moving it up in space, yeah? Vertically upwards. So that's going to be a positive change, yeah? It's a bit more complicated for positive and negative charges. Positive charge experiences so let's imagine that. This is a positive charge. And it's going in line with a field line. So your field lines always do what a positive charge would do. So I have this positive charge and it's going in that direction. So what should my potential be? Increasing? What should my change in potential be? Positive or negative? It's going to be negative. So really, this should be a negative value there. The equation has like a nomenclature where you can kind of like not think about it, not visualize it. You can just put numbers in and you get, if you do everything right, you get the right sign. If you do everything correct, you get the correct sign. But in my experience, if people don't visualize, even with that methodology, they don't get the correct sign. It's best to visualize, yes.
So if we just started with a negative charge, it would be positive?
So if you had a negative charge going in the direction of the field lines, it's like a balloon going uphill. So it's increasing in potential. And so I think about boulders and mountains, and then if I've got negative charges, I reverse my signs on my answers. You know. A 6 kilogram mass is raised 24 meters vertically upwards. What is its change in gravitational potential energy? So I have a 6 kilogram mass. Did we just do one of these? A 4 kilogram mass is vertically upwards. Okay. Yeah, okay. We'll do it. So this is, hopefully I've not messed up on this one. So this is 6 kilograms, and this is 60, and this is 60, and it's raised 24 meters vertically upwards. And then what is its change in potential energy? My change in E is equal to my work done, which equals my force times my distance if they're in line with each other. So my delta G, delta U, my delta U is equal to omega, which equals to my force, which is 60, times my change in that, which is 24. So my delta U is equal to 104.40 joules. And here I have a 2 coulomb positive charge, so this is 2 coulomb positive, is moved 24 down a field line. 24 meters. This is my E in a 4 Newton coulomb. What is its change in electric potential energy? So my change in potential energy is equal to my work, which equals, well, it's not going to be F times D. Well, it would be F times S, which equals, F is of course equal to QE times S. Yeah? Force is the charge times electric field. Yeah? Force is the charge times electric field. So delta U is equal to omega, which equals to Q, and the Q was 2 positive, times E, and the E is 4, and the distance is 24. So this is going to equal 8 times 24. 8 fours are 32. Carry 2, carry 3. 8 twos are 16, and 3 makes 19. So I've added a little bit of complexity here, didn't I? Rather than giving you the force, I gave you the charge and the electric field. Yep. Supposing these guys are not in line, supposing that the displacement is not in line with the force, what I do is I would take the component of the displacement in line with the force. We learned that in Physics 1, didn't we? And so we said, well, this, omega, this work is equal to my change in my potential energy, which equals F times D times the cosine of the angle between them. And we said, oh yeah, if I have a vector force and a vector displacement, I can call that a dot product, yeah? And by the same token, I could have split my vector force up into the mass times the vector field. Yep. Bit uncomfortable with that second one, but it's just because I'm not practiced in splitting my force up into my mass times, W equals mg. It's like, if I'm interested in my gravitational, in my electrostatic stuff, I say, well, and here I'm calling D, I call D and S sometimes because I don't want DD in the end, but whatever. I can say it's the force dotted with D, or it's Q times E dotted with D. And this is what a lot of people learn. QED, quite easily done. That's the old mnemonic we had for it in school. QED, quite easily done. I want to stop for a second. How am I doing for time? Good. And let's do, well, we've done a couple. I want to drive this QED home. Yes, I want to drive this QED home. So let's just jump out of here for a second. Let's put a few pages in. So just get on that. Come along here. Let's have a look. It's never on that page, is it? It's where is it? New slide. New slide. New slide. And then let's go here. Let's go to slideshow. From cursor. Okay. Okay, so let's drive this QED home. So let's do a couple of examples actually. Let's just ring the changes. So the first thing I'd like to do with you is this. I'd like to tell you that the electric field is equal to 2I plus 3J plus 4K. What would the units be for this? Newtons per electric field. Newtons per coulomb. And let's say I move it through my D vector. My D vector equals 3I plus 1J plus 2K meters. And I want to know I can't say my change in, so what has been moved? Let's say a charge has been moved, and let's say 2 positive coulombs. I'd say my change in energy is equal to F dotted with D, which equals my Q E dotted with D. You get that? Because my force is QE. So I say my change in potential energy is equal to my Q, which is plus 2, times my dot product. And I go 2 times 3 plus 3 times 1 plus 4 times 2. Six and 8 is 14 and 3 is 17. You see that? If I want my delta V, my change in potential, then that equals delta U over Q, which equals 34 over plus 2, which equals 14 joules per coulomb. Sorry? 17, yeah, thanks. Yeah, good. Thank you. So that was one little bit. That's another little bit. I can check this because my delta V is equal to E dotted with D. So my delta V is equal to, and it's going to be 2 times 3 plus 3 times 1 plus 4 times 2. So my delta V is going to equal 6 plus 3 plus 8. So my delta V is equal to 17 joules per coulomb. So can you see the game I'm playing there? I can work out my electric potential by working out my electric potential energy and dividing it by the charge. Or I can just work out my electric potential because I know that it's the electric field dotted with D. Yeah, either way. I'm back in this box. You know, F, E, delta U, delta V. I'm back in this box. And initially, I took the force and I multiplied it by a distance. So initially I did that. And in the second step, I took that and I divided it by Q, so I got that. And actually, in the first step, I actually started off with E. I took E and I multiplied it by Q to get F. And then I multiplied that Q by D to get delta U. And then I divided that by Q to get my delta V. Can you see what the game I'm playing there? Whereas I could have just gone like that. Yeah. do another one. E is equal to 4I plus 1J plus 0K newtons per coulomb. D is equal to 3I plus 0J plus 2K newtons per coulomb. Can you find for me, please, delta V? What does delta V equal, just from that information?
Question.
Yep.
Is the distance supposed to have the units as meters per?
Distance is supposed to have the units meters. Thank you. So find for me my my delta V. I'll give you a little while. I'm going to turn this thing off. So let's just have a look about this. So let's have a look. I know that my delta U is equal to F dotted with D. And I know my delta U is equal to, that would be QE dotted with D. And I know that my delta V equals delta U over Q, which equals E dotted with D. Oh, I know where I am. So delta V is equal to E dotted with D. Delta V is equal to 4I plus 1J plus 0K dotted with, I don't write this down often enough, but I just do it, but let's just write it out, plus 2K. So delta V is equal to 4 times 3, remember your old dot product, plus 1 times 0 plus 0 times 2. Delta V is equal to 12 joules per coulomb. They're not hard. You've done all this mathematics before. I mean, this is not hard mathematics. It's just doing the math on the right thing, and that's knowing your terms, knowing your visualization, being able to picture it. The IJKs really help. If I were to say you have a uniform field of, let's say, 9 newtons per coulomb, and I took you on a path that was 4 meters by 8 meters, and I asked you for your change in potential. Now it's E dotted with D, which is, if you like, E D cosine the angle. Delta V is equal to, oh, but I know the cosine of the angle. I can work this out easily. It's going to be 9 times, it's going to be 9 times 4. Because it's the D that's in line with. I suppose you could work out this angle, it'd be a real pain. You could work out this angle, tan theta is equal to opposite, which is 8 over 4. And then having worked out that angle, you basically can then work out the from the angle you can substitute in, but basically what you're going to end up with is it's that field times that distance. You get that from visualization, yeah. Cool. And you're going downhill, so it's probably a negative, which is 9 fours are 36 joules per coulomb, and you're going actually down the thing, so it's a negative sign in there. Can you see how it's all taken care for in the IJK? It's kind of like, in a way, the IJK kind of makes it much more accessible. I'm gonna stop there for a break. So stop.